My name is Kartik. I'm an undergrad at Stanford and studying computer science and physics. Actually, I checked out my Scratch profile for the first time in a few months, and I realized that I'm coming up on like 11 years of Scratch, which is a long time, at least from where I see it. But I was reflecting also because I'm about to graduate, like, where did this whole computer science thing start for me? And I think one of the places it really started was when Brian made me read this textbook. This textbook's called The Structure and Interpretation of Computer Programs. I'm sure many of you have heard like way too much about it from Brian. You'll notice there's this like lambda on the cover. It's like it was Sussman. It's a great textbook. And very recently I learned that Abelson and Sussman actually wrote a companion book, so to speak, called The Structure and Interpretation of Classical Mechanics. You'll notice this textbook also has a lambda on the cover, but actually this textbook is a physics textbook, and it teaches you classical mechanics, like how stuff moves. Like if I throw something, in the air, like what does it do? And it's a wonderful textbook for a variety of reasons, like partially just because everything is beautifully explained, but also because it's in Scheme. Like the whole textbook is actually like written in code. And so you'll notice like these math expressions are Lisp expressions, and you can do all sorts of fun things with them. For example, if you write the expression like sine of x, you can take its derivative and it'll give you cosine of x. And calculus is the bread and butter of physics, and being able to do calculus on your Scheme programs is just hugely empowering and fundamental to how this book works. Um, so I took classical mechanics maybe a year ago at college, and I came across this book, and I got hugely excited because this idea of doing calculus on your computer programs is just fascinating to me. It's actually its own programming paradigm. If you believe Wikipedia, it's called differentiable programming. And the idea is you write a computer program and then you take derivative. Why is this useful? Well, okay, in all honesty, people care about this because it has applications to machine learning. It turns out that if you can take a derivative of a function, then you can kind of walk downwards along it and optimize it. And optimization is like really good for capitalism, as it turns out. So that's one use of being able to take derivatives of your computer programs. But I think there's also like a really there's a very snappy thing that can be done here. And so I wanted to show you like a little demo of my vision for what differentiable snap could do. And this is like a little demo I whipped up like a couple of summers ago. It's called TurtleGrad. And it's not blocks, I'm sorry, it's just text. But this is a program that I think all of us have written at some point. You set a variable, and then you have a loop, and you move forward a bit, and then you turn, right? And you get this nice like shell. And suppose I ask the question, like, what if I wanted the shell to be tighter? Or what if I wanted it to kind of be wider? Like what parameters would I change, and how much would I change them by? Well, that's exactly the kind of question that calculus lets you answer. And if I could take a derivative of this computer program, then I might be able to twiddle these numbers to do that. And being able to take the derivative is exactly the power we need. So I implemented that, and now I can actually grab one of these turtles and drag it. And what happens is that you see this number 90, like this is how much the angle changes. It turns out that's the important parameter to control the like tightness of this curve. So I can just click it and drag it, and it'll figure it out for me. And the reason this works is it's just taking the derivative of this program and then doing gradient descent. And there's all sorts of fun you can have with this. So, here's a program I wrote that like draws a piston. So it moves, it turns, and then it draws a square. And you might ask, okay, well, okay, I can like click and drag this, and you'll notice that this changes the initial angle it turns before it starts drawing the piston. And that's all well and good. I can also grab like the top of the piston, and I can pull it up and down. Oops, got stuck there. I can pull it up and down. And it kind of reverse engineers through all of this like pretty complicated math, but essentially for free, to figure out what the angle needs to be. And it lets you kind of program in this like kind of really fun bidirectional way. One last example. So here's like a cannon. You kind of, it draws a parabola. Well, I can grab the end of this and I can kind of drag it around and I can see like how I change the initial angle and the initial velocity to get this cannon to fire at different places. And all of this is essentially for free if you can take derivatives. So this is kind of a very wacky hypothetical idea. And I am intentionally trying to be a little provocative with this, but I think differentiable snap would be very cool. If you're interested in this, I have a clever way to implement this, I think, which uses continuations. There are many ways to reach me. Just send me an email or talk on the forum, and I'm happy to talk more about this. But there's my provocation.